paper that's, yeah, the one that's in the value of statistical life. Okay, so good morning. So there's sort of two things that we're going to cover today. The first thing is going to be very fast, which is just we learned about like regression and sort of learn about statistical significance. And so I want to so the first thing I want to do is sort of discuss how you would actually read a table that reports regression results in a paper, since most of the papers that are on syllabus will have tables that look somewhat like this. In fact, this table is taken from a paper that's in the next topic, which we're talking about. So the second thing that we'll talk about is the value of statistical life. So conceptually what that represents, and then how we create estimates of the value of life or the value of statistical life. I guess so. Before we start that, when we ended last time. I think there was, we had this discussion about whether or not like the fact that Steve Jobs died the day after they released the latest iPhone was whether we would view that as being statistically significant or not. And so just to recap, so the entire underlying idea behind testing for statistical significance is the following. So what you're trying to do, is you're trying to answer the question of whether or not the pattern you observe in the data is just due to chance or whether it represents a real relationship, right? And so at least one, if not more, of the groups actually calculated that if the probability that Jobs died on any given day of the year was always equal, so that means it would always be equal to 1 over 365, then under that, so if that were true, that implies two things. So first of all, it implies there'd be no relationship between the date they released the iPhone and whether or not he died, because he had an equal probability of dying any given day. So there would just have been chance that he happened to die the day after they released the iPhone. So that's encapsulating what we call the null hypothesis. That's the hypothesis that you're trying to test. And then the second thing is that it implies that there was only a 1 in 365 and maybe like a 1 in 180 if you want to sort of think about a 2-day window. So let's just say we're thinking about a 2-day window. So there's only a 1 in 180 chance that he would have died within a 2-day window around the date that they released the iPhone. 1 in 180 is not, those are not very good odds. If you were betting on an event that was going to happen only 1 out of 180 times, you wouldn't be willing to bet very much money, or you basically require a very large payout. So we can conclude one of two things given the observed data. Either we just observed a very unlikely event, or something was wrong with the probabilities that we initially calculated. And when we say something is wrong with the probabilities that we initially calculated, we're saying is the hypothesis that we imposed when calculating those probabilities is false. It's not true, right? So hypothesis there's no relationship between his death and at least the iPhone, or rather this iPhone and his death, would be false. And so then we would reject that hypothesis and conclude that there is a relationship between his death and the fact that they just released the iPhone. Statistical significance is the thing's a little tricky here. One thing's a little tricky is it's different than sort of asking whether or not the relationship that you observe represents a causal relationship. So, if you think about the Facebook and the voting example that I mentioned a couple lectures ago, right? That essentially the number of likes that a candidate gets on Facebook is predictive of whether or not they win, right? So Facebook probably has a lot of data, because they collect a ton of data. There's like lots and lots of candidates in any given year who are running races if it's an election year. So that relationship is statistically significant. Like it's not just due to chance that the candidates who had more likes were more likely to win. That's an actual relationship. It's not a causal relationship. It doesn't say that if you go and enlist hundreds of friends on Facebook to like you, that you're going to necessarily like win a congressional race or become president or anything like that. But it is a relationship, doesn't have a causal interpretation. So you don't really want to think of statistical significance as being directly linked to thinking about causality. They're really sort of two different questions. One is whether or not the relationship that you observe in the data actually represents some true underlying relationship between the two variables, and then the question of causality is whether or not you can then interpret that relationship as being a causal relationship between x and y. Okay, so in terms of applying what you learned about regressions, what you'll often see is a table that looks something like the following one. So typically, what's going to happen here is there are different rows and separate columns. This doesn't always have to be the case, but usually each column is basically going to represent a separate regression. So you can see that there's 3 columns here. So what that implies is that there are 3 regressions. So the first regression is going to look something like this. So it's column 1. What that's reporting is essentially a regression of yi is equal to beta naught plus beta 1. This is going to be leukemia risk. So this is like variable plus beta 2 times lot size plus beta 3 times lot size squared, and so on until you get to the last variable here, which I'll call beta k, which is potentially like this circle county dummy. And then there's going to be some symbols. So they're running a regression that looks like this, and then what they're reporting in the column is basically the beta coefficient on each of the variables here. So like that first column, the first row is giving you the beta coefficient on leukemia risk, so it's minus 0.123, and then in the parentheses is the standard error. So if you wanted to compute the t-statistic to do a test for statistical significance, you have to take the coefficient and divide through by the standard error. In that first row, it's like 123 over 13, so your t-stat is going to be like 9 point something. Remember, the rule of thumb was it's over 2 in absolute value and it's statistically significant. So in this case, we would conclude that there is a statistically significant relationship between leukemia risk and whatever the dependent variable is. So we're going to talk more about this particular study, not today, I think it's by Monday. In this case, what he's studying is essentially the relationship between housing values and a bunch of other variables, but the one he's most interested in is leukemia risk. So the question is essentially, like, are housing prices lower in these areas where there's higher leukemia risk? You would tend to think, yeah, people are probably not going to want to live in those areas because who wants to get leukemia? And that's in fact what he finds. So the exact interpretation of that coefficient is that holding all of the other variables in the regression constant, so actually leukemia risk, so I think it must be like a 1 point increase in the leukemia risk variable, which might actually be defined sort of depending on. So that's probably that's calculated at county level. So there's 2 counties in this data. So I actually would have to look up exactly what the change in leukemia risk is between those 2 counties. But at any rate, one unit increase in that leukemia risk variable is associated with a 12% decline in housing values. So the reason that we can interpret it as a 12% decline rather than like a $12 decline is that if you look in the table notes, what we have here is actually, so the regression is actually, it looks like the log of y regressed on all of these variables. yi is like the sales price of house I, and so it's actually the log of the sales price. Whenever you see, whenever you see a dependent variable, a left-hand side variable in regression that's been logged, you can then interpret the coefficient as a percentage change in that variable, or percent change in that variable, rather than like a level change in that variable. And you'll often see that, like in a lot of the regressions, you'll see that they just log the variables, in part because it's just easier to interpret. Like if I told you there's a $10,000 decline in housing prices, you might say like, well, I don't know whether that's sort of large or small. It's going to depend on what the average housing price is, right? If houses are going for $50,000, that seems really large. If houses are going for $1 million, then it doesn't seem all that large. Oh, yeah, that's a good question. So basically what he wants to do is the author wants to account for the possibility there might be a nonlinear relationship between lot size or between building age and house prices. So if you just put in lot size, then what you're saying, what he's saying is that essentially it has to be the case that, so this is sales price, and then lot size. So if you just put in lot size, then it would have to be the case, like even if the data sort of looks, say, something like this, which would kind of suggest there's like this upward, that there's this convex relationship between lot size and sales price. The linear regression, it's still, you force to fit a straight line to that, so I mean, wouldn't fit that straight line into a better fit, but it still would be like, this is trying to fit a straight line to the curve underlying relationship. Once you put in the quadratic term, then it's able to actually fit like quadratic curves to that relationship. So it's more flexible in the case in which there's a nonlinear relationship. So the other variables that are in there are not, that's a case where he's adding controls because he thinks that there's going to be differences between houses that are in the high leukemia risk area and houses that are in the low leukemia risk area. And so he wants to try to control for those differences to the best that he can. So he has things like the lot size and how old the house is, the amount of square footage in it, which is the floor space. And then he ends up adding these other variables, which are down here as well. I'll talk about in a second. But the motivation, again, is not that he actually sort of cares specifically what the coefficients on those other variables are. He's really only interested in the coefficient of the leukemia risk variable. But he does need to try to control for those other variables to try to sort of eliminate omitted variables bias that exists between when you're comparing the high leukemia risk area to the low leukemia risk area. So that's like the first regression, and then in the second column, so that's another regression. What he's doing is he's like running the same specification, but he's adding additional controls. And so you'll often see this thing where they'll put basically like they'll make indications in each of these rows for entire sets of variables they're going to add. So class dummies, I'm not quite sure. I assume it's probably something related to so the type of house that it is. But certainly like year dummies and month dummies are pretty straightforward. So the year dummy is just going to basically put in a separate dummy variable for every single year that's in his data set. He's got, let's see, sample contained sales of single family residence from 1990 to 2002. So he has 13 years of data in his data set. So he's going to end up putting in like 12 year dummies. And those are going to control, or those are going to basically account for any time trends in sales prices that might be, that might exist in the data. He's also putting in month dummies, so I believe the month dummies are going to be like month of year dummies, so it'll be like 11 dummies, not 11 times how many years he has, or 13 dummies, because he's basically just trying to account for like seasonality here. So you have like a dummy for January, a dummy for February, March, and so forth, and those are going to indicate the month in which the month of the year in which the house was sold. So he adds in basically these other controls, and then he so basically the way that you look at this table would be that he initially estimates a 12% decrease in the high, or he estimates that sales prices are 12% lower in the high leukemia risk area relative to the low leukemia risk area. That's in column 1. He's controlling for several factors there. Then he adds these additional controls, which are these class year and month dummies. When that happens, then the difference in housing prices actually increases. Now it's like about 15.5% instead of like around 12%. That's in the second column. And then in the third column, he adds even more controls, which are in here. So he doesn't say SE 49.22. So I think what he's doing there is adding separate fixed effects for every single house. So the in fact it has to be. So what's happening in that last column is that now, since he's got data on these houses over a 13-year period, he could actually put in like a separate dummy variable for every single house, and then when a house is sold more than once in his data set, then he can sort of look at how prices change for that house from, say, if it was sold in like 1995 till 2000, if that were when the second sale was. The reason that so what happens here is you can see that all of the coefficients on those other variables drop out on like lot size and floor space and building age and so forth. The reason for that is that now that you have a dummy variable for every single house, those variables are all redundant in the sense that they're perfectly collinear with that dummy variable. So the way that you want to think about it is like if you put in an indicator for a given house, what you're going to capture are all of the factors about that house that don't change over time, right? So the dummy variable is basically an indicator for that house. It can sort of absorb anything about that house as long as that factor doesn't change over time, because it's an indicator that's going to be 1 for that house, but it's 0 for all other houses, but is not going to change at all over the sample. So because of that, it's like redundant to put in the lot size, say, of the house, because the dummy variable already captures that, since lot size is something that doesn't change over time. And B, if you actually try to do that, it turns out that when you run the regression, like Stata or whatever statistical package you're using is going to drop that variable because there's perfect collinearity between the two variables, and so the regression actually wouldn't work. So once he does that, all of the variables that are basically fixed over time get dropped out. You can still keep the year dummies and the month dummies in there, though, because those are things that change over time. The year dummies is something that it's going to be 1 in a given year, 0 otherwise. Leukemia risk itself also is changing over time, so that's why that coefficient stays is still like that's why he estimates that coefficient, which is the one that he wants. And there you can see that then the coefficient changes to like 14 percentage points from 15.6. So overall, sort of the takeaway, if you look at this table, would be that there's this pretty stable relationship in general. The high leukemia risk area sees housing prices that are about, I guess you'd say like maybe 12 to 16% lower than the low leukemia risk area. And sort of more importantly, that coefficient doesn't seem to change too much as he adds more and more control variables. So like you're never going to be able to add so many controls that you couldn't think of like another omitted variable that you would like to put in the regression. So you can like no matter how many controls you have in the regression, probably somebody, if they think long enough, unless you have like a true randomized control trial, somebody if they think long enough can come up with like another variable that they think you should put in the regression, but you either haven't yet or that you simply can't because it's not something that is in your data. that being said, if you can show that when you start out with relatively few controls and you add more and more controls, the coefficient doesn't really change that much, then that's at least suggestive evidence that even if you could add these additional variables that people are coming up with that you don't have, the coefficient would still remain kind of stable and therefore might represent a causal relationship. Okay, so we're going to talk more about this paper later on Monday. Hopefully that will make more sense to you. Okay, so the next topic is the value of a statistical life. And so this is a pretty important topic in the sense that when we think about a lot of the benefits of policies that are either sort of related to the environment and that might improve population health or that are directly related to health, the benefits of those policies are going to mainly accrue in the form of either reduced morbidity, which is like reduced illness, or reduced mortality, which is of course reduced death. And so if we want to think about how we would value those benefits, then we need to come up with a dollar value for basically a safe life. So just begin is sort of a quote that I think is kind of amusing and does have some relevance to the topic, which is an economist knows the price of everything, or someone who knows the price of everything, but the value of nothing. And I think this is sort of a topic where many people would argue that assigning a value to a life represents basically like a reductio ad absurdum argument, proving that economists go too far putting prices on things. So economists love to sort of create markets where there weren't markets before, and sort of think about either prices that are directly reflected in those markets or things we call shadow prices, which are like implicit prices that are put on things. But once you start talking about putting a price on life, that's where a lot of people start to get frankly kind of offended. And they argue, well, isn't life priceless? Somebody basically you're never going to be able to offer somebody enough money so that they would say like, yeah, go ahead and kill me because I want money because after you're dead, really money isn't too useful for you. So despite these facts, the EPA does in fact assign a price to life. So it's probably in the $7 to $8 million range now. It was $6.9 million in 2008, and they update it from time to time. So you might wonder, certainly if you were curious about thinking about how the EPA would decide whether or not policies are worthwhile, you might wonder how they calculated this figure. And this is all before your time. In fact, it's even before my time. But there was a show, there used to be a TV show about this.
A man barely alive. Gentlemen, we can rebuild him. We have the technology. We have the capability to make the world's first bionic man.
So you go back to the 1970s when that show originally aired. So it was called The $6 Million Man, and the premise was that it costs $6. The guy gets like an astronaut or something like that, because critically injured in an accident, and they're like, okay, well we can save him. We'll just make him into a bionic man by putting all these bionic parts on him, and it'll cost $6 million, which back then was like a lot of money. So I think the sort of the most amusing part for me about this clip is that with the power of compounded inflation since the 1970s, the $6 million man is now actually worth less than the average American. Right? So the EPA is putting a $6.9 million price on the statistical life. So that also implies that even if he's supposed to have like super strength and stuff because he's bionic, but even if you weren't better, faster, or stronger, you'd still want to basically invest the $6 million in rebuilding him, because even if you're just an average person, we're saying that his life is already worth more than $6 million anyway. So in terms of thinking about how the EPA actually calculates this figure, the $6.9 million figure, there's several possible ways that you might think about doing it. So I think one of the things that would occur to a lot of people like immediately is to think about essentially like the net present value of somebody's discounted lifetime earnings or something like that, right? And that's something that sometimes will sort of come up in court cases too when you're talking about like negligent death or something like that. So you could essentially figure out like how much somebody's earning this year and project how much they're probably going to earn over their entire career, and then discount that back into current dollars and use that as sort of the value of their life. That's not really. There's actually not like a strong economic argument for doing that because that's just kind of showing what their earnings power is, but it's not really answering the policy question of like how much as a society do we think in general we should spend on trying to save a life or a statistical life. Nor is it necessarily sort of showing anything about their preferences to try to avoid death by making investments in safety. So that's not how like most economists would argue that you should calculate the value of statistical life, and it's also not how EPA does it. So rather, the way that it's done is basically what you do is you look at willingness to pay to avoid relatively small risks, and then you basically like rescale that willingness, that dollar value, that willingness to pay up to like a large risk. So you're going to look at. The idea would be like you look at how much somebody would pay to, say, decrease their chance of dying by 1%, and then you would take that amount and multiply by 100 to scale it back up to 100% chance of dying. Now, again, that's not to say that what you want to interpret the VSL as is, so when we talk about the value of life, we really mean the value of statistical life. The way that you want to interpret this is that you're looking at relatively small changes in risk and people's willingness to pay for them, or willingness to pay to avoid increases in risk, and then you're sort of rescaling that up. We're not saying like how much would somebody pay to avoid certain death, because that's like not something that people generally face, and it wouldn't be all that informative in that it's just going to be probably bounded by their ability to pay rather than any sort of preferences they might have. So the way that we calculate it is basically it's going to be the marginal willingness to pay for a risk reduction divided by the amount of the risk reduction, or alternatively, it's going to be the marginal willingness to accept for a risk increase divided by the amount of the risk increase, right? So it's just the same question of willingness to pay versus willingness to accept. If we're talking about something that's a good then that you don't currently have, then it's going to be your willingness to pay for that good, so risk reduction is something that you like. If it's